I'm going to let you in on a secret. This is my next get-rich scheme. This right here is what we call in science an ice cube. And ice cubes are 0 calories, right? No, actually they're not. Ice cubes are negative calories. Because if I take this ice cube and I put it in my body, I've got to bring it up to body temperature and melt it. And that requires calories, energy from my body. So I'm going to invent the ice cube diet, and that's how I'm going to get rich. I have to just trademark it. And don't share my idea, because that's how I'm going to get rich. All right. Let's talk about Well, hey everybody, hey, Mike here. I guess I'm still with you. It turns out you can't copyright or trademark ice cubes, but okay, another idea might pop up. So today we're going to talk about heat, and we're getting into the chapter 5 of the OpenStax book, where we talk about heat and transfer of heat. Now, there's basically 3 ways heat can go from place to place, object to object, and that would be, one of those we'll focus on more than the others. So the first would be these first 2 we won't talk about, I'll just mention. Convection. So fluid carries thermal energy from place to place, whether that fluid be air or any other kind of fluid. That's called convection. Radiation we will talk about in about another chapter, and you might be familiar with the fact that there's light waves have energy. Specifically, infrared radiation is radiated heat. Today we're going to talk about conduction. So I take, like me swallowing the ice cube, I take a cold body and I put it in touch with a warmer body. They will trade heat from cold body to warm body to cold body until they become the same temperature. So that is conduction, and that's what we're going to focus on today. And so one of the units of heat that we're going to focus on has to do with conduction. So the definition of what is a calorie. And this is, by the way, related to your food calories. So that is the amount of heat that's required to raise the temperature of water. Why water? Well, because we use water as a standard in a lot of different things, right? That's what we base our Celsius temperatures on. And so the unit of a calorie is how much heat you got to put into water to raise a gram of it. Now keep in mind, the nice thing about water, as we will find out later, is a gram, due to its density, is about a milliliter of water. And so that's what a calorie is. That's not a food calorie. A food calorie is a kilocalorie. And in the old days, and we've gotten away from this, there was lowercase c, which was a calorie, and then a kilocalorie was uppercase c. Now we just use the term kilocalorie. Another one is joules. So you might see either of these 2, and a joule is smaller than a calorie. It's 4.184 joules is a calorie. And so that's the definition of joules or calories. These are called heat, units of heat, and we're going to use those units to solve different problems. So the next thing I want to talk about is the fact that the definition of a calorie is actually a heat capacity. So next thing is called specific heat capacity. It has the symbol C, and that is the amount of heat required to raise the temperature of anything by a degree C. So the heat capacity, or by the way, there's about 3 different names. Specific heat capacity, or you might hear it called specific heat, or you might hear it called heat capacity, but that is C is the symbol of it. And so if you're talking about something that isn't water, it'll have, you go look up its C value, and it will tell you how much energy is required to heat it up, a gram of it, by a degree C. So the funny thing is, water, liquid, the heat capacity is the definition of what a calorie is. It's 1 calorie per gram per degree C. Now, quite often for specific heat capacity, they use units of joules. So the next values I'm going to show you, you'll find in almost any textbook. And I want to stop after this, right there. do you notice the difference between water in any of its phases, especially liquid though, and something like aluminum? So if you took water right there, that means 4.184 to 0.9-ish. That means that roughly what, 4.5? Takes 4.5 times as much energy to raise the temperature of water than it does aluminum. So we say that water has a greater heat capacity than something like aluminum. Now you got to watch out. Heat capacity and temperature change are going to be inverted. So if I put, say, 10 joules into a gram of water, the temperature change of water would be less than the temperature change of aluminum. And aluminum actually is pretty large in heat capacity due to compared to some other metals. So iron, you see, that means that it'd take less energy to heat up iron. Copper, and now, you know, you got different goals in life if you're going to be cooking with, say, an iron skillet, then an aluminum pan, then one of those fancy copper ones. And so the lower the heat capacity, the greater amount of thermal conductivity. And so those heat capacity is how much heat it will hold if you put heat in before it changes its temperature. And an interesting thing that I won't go into much detail about is that the denser it is, the more thermally conductive it is, and the smaller the heat capacity. So that's just a little weird trend. It must be that the spaces between atoms are not as great and there's nowhere for the heat to be kind of trapped there. And gold is one of the most thermally conductive materials there is, and that's why they use it in the electronics business and all sorts of stuff. So, okay. So we have those, and you should be able to look those up when we solve problems, which we're going to do in a little bit. But first, we must know what our arsenal of weaponry is. And the one thing that's going to get you through any problem is that equation right there. Q, heat, can be in joules or calories, it could be either, is equal to MC delta T. It kind of sounds catchy, like some sort of hip-hop star, you know, like somebody would have like a calorimeter hanging around his neck. That's, if I do a hip-hop act, I'm going to be stage name MC delta T. But anyhow, that would be MC is mass in grams, C is in joules or calories per gram per degree Celsius, and delta T is the temperature change in degrees Celsius. Or you know what's funny? It would also be in Kelvin. Kelvin temperature units are spaced the same way as the same distance as degrees Celsius. So it doesn't really matter if it's a change in 10 degrees Kelvin change is the same as 10 degrees Celsius change. So we're going to use that to solve a lot of problems. And then what we're going to have to do also is simplify the universe into this. We're going to take the whole universe and we're going to say every problem involves heat flow from either the system. Now, what could be the system? It depends on how you define the problem. The system could be the ice cube and I could be the surroundings. Or I could be the system and the ice cube could be the surroundings. But either way, Q is going to flow one way back and forth. And if we were keeping track of the system, you could see here that delta T, now let's talk about anything delta. Delta T equals T final minus T initial. And so in this case, the final temperature of the system, having had received some heat, would be greater than the initial, and that Q direction into the system would be positive. If the system lost heat, delta T, which is T final minus T initial, delta anything is final minus initial, would be negative. And so sometimes you're going to have a sign in the equation Q equals MC delta T, depending on what the sign of the delta T change is. So if something loses heat, its delta T is going to be negative. So warm body cools from 40 degrees to 20 degrees, that's a delta T of 20 minus 40 or negative 20. Or room temperature body heats up from 20 degrees to 80 degrees, that's a delta T of 80 minus 20 or positive 60. So sometimes depending on the wording of the problem, Sometimes there's a sign in there. Speaking of problems, let's get at it and solve one. All right, here we go. Barney drinks 4 liters of water. How much heat? Okay, so now when I see, you gotta read these like a computer, you know, heat, Q. There you go. I saw the word heat. That's the symbol for heat is Q. Is required to bring his body to bring this cold water. By the way, that's about temperature of refrigerated water. If you've got a bunch of water in your refrigerator, it's about 42 degrees. It's 5 degrees Celsius. Your body temperature is 37. And now, actually, we're off the hook here when it says required. That kind of gives you the direction that there's, when we say heat evolved or heat absorbed or heat required, now we don't have to deal with negative signs because you can't require negative so many joules or calories. But I think you can see that when I saw the word heat, it's Q equals MC delta T. I can tell you right now that delta T is going to be 37 degrees C minus 5 degrees C equals 32 degrees C. So I got that figured out. What's C? I'm going to go look it up in a table. It's water. 4.184. Now it's best to keep track of all the units, and I'll show you why. Because this better have units of heat when I get done with it. Now the one thing that's kind of tricky, 4 liters is 4,000 milliliters equals 4,000 grams. There's my M. And by the way, that's a lot of water. That's a little over a gallon. I guess you're supposed to drink about a gallon a day depending on, you know, your circumstances. But, you know, that's a little bit more. So Barney overdid it a little bit. But now let's go and put these together. Now I'm going to be real careful to make sure that I keep track of all the units. So Q is the only thing missing, and that's good because they say how much heat is 400 grams. Oh, excuse me, 4,000 grams. Times 4.184 joules per gram per degree C times 32 degrees C. Now let's go ahead here, not rush it too much. Let's take a look at units and what they're going to do. Grams, cancel. Degrees Celsius, down in the numerator here, cancel. This is going to have units of joules. So let's go crank it out. Okay, 4,000 times 4.184 times 32, and holy cannoli, that's a lot of joules. But let's convert it to calories. So it is 535,000. 552 joules. Now, as we stated before, if we want to convert to calories, there's 4.184 joules in a calorie. And now you're still probably pretty flummoxed, like that's still a lot of calories. 1,000 calories is a kilocalorie. That's what a food calorie is. And so I am not going to have that incredibly large number of calories, but it's going to be something. 4.184 divided by 1,000. 128. Kilocalories. Remember, a food calorie is a kilocalorie. And actually, you know what? Two significant figures, I'd probably call that 130 kilocalories. Hey, you know what though? That's still something. That is more than an apple. It's about a third of a package of ramen noodles. But it's something, and you didn't do any work except use your body's energy to expend it. So maybe I'll do the cold water diet and I'll try to trademark. No, that ain't gonna happen. So, all right, that was a relatively easy one. Let's do a bear of a problem next. All right, just look at all those words. So what's going on here is Bubba is lucky enough to have a 1981 penny. Now, if you know anything about pennies, or you collect coins, and if you don't, that's fine. I'll bring you up to speed here. What's going on here, up until 1982, pennies were like 95% copper. So let's just make this, hey, if you're going to be an engineer, we need to make some assumptions. Let's say that we can deal with the fact that 5% of it was zinc, and let's just say that that has about the same heat capacity as if it was pure copper. And they were worried about the fact that copper became more valuable than the penny and people would melt a bunch of them down. So they now are 97.5% zinc and plated with copper. So, all right, great. So let's read this. So we got a mass. There's an M. Assume pure copper. Bubba heats a penny to a temperature of 490 degrees. Wow, that's a T. Then he drops it into 50 milliliters. Now that's 50 grams of water. There's another M. At 25 degrees C, at what temperature will the two come to thermal equilibrium, which would be the same temperature? So it doesn't really matter what we call system and what we call surroundings. We could call this the water, and we could call this the penny. But once again, it's the same equation, and it's Q equals MC delta T. But here's what we got two things now. And we're actually going to see where they come to thermal equilibrium. Means that they're going to come to some temperature between 490 and 25. Now I'll give you a hint. It's kind of nice to prejudice yourself a little bit with these problems, because I can tell you that the 50 grams is way more mass than the 3.11 grams. And I also know that on a heat capacity scale, water's heat capacity is way bigger than copper's, 0.385. But here's how we're going to set it up, folks. And it's going to take me a few pieces of paper. Q transferred from the water is going to be equal to Q lost, I should say, Q gained by the water is equal to Q lost by the copper. Now, here's the thing. You need a negative sign in here somewhere, because heat's flowing a different direction from the water than the copper. So you need to either have a negative sign here or a negative sign here, and whereas negative signs didn't matter in the last example, it does here. But I promise you it doesn't matter as long as it's in one place, because you see, if you're the copper, you're losing Q. If you're the water, you're gaining Q, so that's different direction. And what we could say is, well, that's equal to M, how about if I just abbreviate water as a W, M water, C water, delta T water equals minus M copper, C copper, delta T copper. Okay, let's fill in some things here. I know that that mass is the mass of the copper. There's an M. I know that mass is the mass of the water. I know I can go look up heat capacities from my table here. And so I can get through the M and the C part. So M water, that's going to be 50 grams. C water, I look it up in the table. It is 4.184 joules, and then there's copper. 4.184 and 0.385 for the copper. 4.184 joules per gram per degree C. Delta T, now this is the tricky thing. I don't know what they end up as. That's the whole point. It's final minus initial. So we're going to calculate the final for both. And this is going to be x minus initial. Now the water was 25 degrees C. That's all equal to 3.11 grams. 0.385 is what the table says the heat capacity, joules per gram per degree C, times delta T is, oops, negative. I had to put the negative in there. X minus 450. Now, you know what I say, folks? It's great to keep track of units, but would you agree with me that X is going to be in degrees C, and this is going to be a lot more mentally healthy for us if we just lose our units for now. 50, I just wrote them out of habit. 4.184 x minus 25 equals minus 3.11 times 0.385 times x minus 450. And the name of the game is we got an algebra problem and we're going to solve for x. Now let's clean that up a little bit. Order of operations, let's multiply these two numbers together. So, and then we can do the whole distribute, right? Times 4 I just use a math term. So this is 209.2 times x minus 25 equals minus 3.11 times 0.385, 1.19735. That's a lot of digits. I'm gonna truncate that a little bit, so I know I'm losing a little bit of precision there. 450. I know it's ahead, that's why I'm doing that. Now what I'm going to do is I'm going to distribute. Now remember, the name of the game is solve for x, and x sure as hell better be in between 450 and 25, or else I jack something up. Usually it's the negative sign, which is to blame. So here we go. 209.2x minus 209.2 times 25 minus 5,230. I hope you're doing this along with me because this will be good practice. Equals minus 1.197x minus 1.197 times 450, 538.65. Okay, why don't we get all my x's on one side by adding to both sides 1.197x and that would be wonderful. So I know, and then don't daydream because that's when you goof stuff up. So 209.2x plus 1.197 is 210.397x minus 5,230 equals negative 538.65. All right, let's get all my numbers that aren't x's on the same side. And then, hang in there. So what I'm going to do is I'm going to add to both sides 5,230 and now we end up with 210.397x equals, I don't know yet. Okay, so minus, only a couple steps away, folks. 4,691.35. Oh, my third piece of paper. Oh, good. We're at the end. X is what happens when I divide 4,691.35 divided by 210.397. And 4,691.35 divided by 210.397. Good news. I know I did something wrong, and I can figure out what I did wrong. And it's right here. You know why? I'm going to keep this. I ain't going to edit this out. Negative, double negative, that's a positive. That's a positive. And so when I took the negative 1.197, I jacked it up because I should have had that be a positive number right there. See, that's a good thing. You're going to goof up. Hey, look, I've been doing this 27 years. I just goofed up. So now let's trickle this down to still, when I add these two together, this would be 210.397x equals a bigger number. It can't be less than, heat didn't just go nowhere. So back to my unjacked up result, 538.65 positive, sorry, that was loud, plus 5230, 5,768.65. Now if I divide that number by 210.397, I get 27.4. Now, that might be kind of a number that might not seem realistic, but remember, the water was more massive by a lot. You know, that way more than 10 times. So the water outmassed the penny by a bunch, 16 times. Naturally, water has a higher heat capacity than does copper, more than 10 times. And so the fact is, yes, my temperature final was in between 25 and 490, way closer to the 25 though than the 490. And that, I know, go crank it through again if you have any doubt. And I know I jacked up my negative sign there, you know, but that's the good news, is a lot of times when you jack stuff up, you can unjack it up. So there you go. That, my friends, was the expert level. You just leveled up if you can do one of those. Bling! So give more of them a try and practice. And next time we will talk about where that heat comes from with things and the processes and their heat change of those. So till next time, take care.